My name is James Etter, Draeger Safety Regional Sales Manager for Responder Market, which is fire service, police, and the mining industry. Today, I'm at Station 322, and the purpose for this training today is to train the fire department on some of the Draeger gas monitors that are being utilized within county fire. I'm here today to give better understanding to the firefighters so that they know how to use the meters and understand basic gas detection 101. But this does not take the place of reading the instruction manual on all of these meters. Draeger also has training CDs that we use that you can put on a laptop computer to give yourself total knowledge of the gas monitors and all the liability that comes with them if they're not properly maintained, calibrated, and bump test, as well as making sure that you've got a good battery and a good power supply to get you through a given incident. First off, we're going to be touching base on 3 instruments: the multi-warn 2, the mini-warn, and the exam 3000. And essentially, these 3 meters, which I have on the table here, all pretty much do the same thing. They monitor for a lower explosive limit for combustibles. They're all calibrated mostly to methane, which is generally your calibration gas for combustibles. They monitor for oxygen in the percent by volume range, carbon monoxide in the parts per million range, and hydrogen sulfide in the parts per million range. CO, carbon monoxide, H2S, hydrogen sulfide are both combustible gases, but they're very toxic at very, very low concentrations. So the idea is to protect the firefighters from the very low, minute toxicity exposure of carbon monoxide and hydrogen sulfide. And that is the goal of these instruments. Oxygen obviously is there to make sure you have plenty to breathe, and there's alarm thresholds to protect you so you can get to a fresh air environment. On the combustible detector, that is to protect you from explosions and an explosive environment. It is not necessarily there to pick up minute traces of combustibles, but more to monitor in the fresh air up to the explosion range of a combustible gas. And that's the intent of the gas monitor.
Monitor prior to going in. Don't forget to monitor in steps all the way through. Okay, there's a 14-year-old boy that's lost somewhere in there. His buddies were in there with him. They decided to play a prank on him, and they disappeared on him. We've got the boys already on the side, but there's still one left in there. Last time they talked to him, he was fine. He was talking to them, and then they bugged out on him as a prank. So they all made it out, but he didn't. So as far as we know, he's in there somewhere. But he is ambulatory, he's able to talk and everything. They played a prank on him and got him lost, and then they bailed on him. Okay?
Here is a chart that I wrote up on your scales for the 4 gases that are on your instruments. The LEL scale on the instrument is percentage of the lower explosive level or lower flammable level. You'll see LFL or LEL. They both, again, are synonymous. What this means is the lowest amount of gas or vapor to ignite. So 0 means you have no gas, no vapor. But once you get to 100% of the lower explosive level on these instruments when they're calibrated to CH4, what that means is that if you get up to 5% by volume methane, that equals 100% of the lower explosive level. So 5% by volume methane in this room, mix it up, lots of convection. I can technically get a heat source of 999 degrees with the right amount of air to create an explosion. So if you want to look at this in perfect math, 1% by volume of CH4 is 20% of the LEL. 2% by volume of natural gas is 40% of the LEL. 3% by volume is 60%. 4% by volume is 80%. 5%, you've hit your lower explosive level, and that is your explosion point. The whole idea of these instruments is to alarm you at 10% of the LEL, which gives you a 90% safety factor to the explosion point. Okay? And there's also a secondary alarm that's also on this scale, and that's also true with these three scales, which is a more severe alarm. That would be 20% of the LEL, giving you an 80% safety factor. And the reason that the alarms are so far down scale is because even though we're calibrating the instrument to CH4 or natural gas or methane, you could be out on a freeway monitoring gasoline vapors, and if the instrument's telling you, yeah, I've got 10% of the LEL, you might have 20% of the LEL. So it has to safeguard you on the low end of the range because of different combustible gases that will be in the environment or could be in the environment. And remember, I've said it once, I'm going to say it another time, this scale, the hot wire sensor, the Wheatstone bridge, will burn any combustible gas that's present or gases that are present. It could be an accumulative combustible gases or vapors, but they'll all burn on the sensor. It just happens to be that we calibrate it to methane, so that means if you're in a methane environment, that the reading on your instrument should be a very accurate reading. If it says 23% of the LEL, you're in 23% of the LEL if you've got a good calibrated meter. Yeah, your number 2 scale is oxygen. Percent by volume is what I've noted here. Percent by volume, the amount of oxygen per volume of air. Air is basically made up of essentially 21% oxygen and 78% nitrogen. Okay? So what we're doing is we're monitoring a scale of 0 to 25%. Generally, in fresh air, we're breathing 20.9% by volume oxygen. Our concerns are if we have a deficiency of oxygen, we need to have an alarm, and that alarm will come at 19.5%. But we're also concerned about enrichment, and that's why our scale goes to 25 from 20.9. If you see your oxygen starting to increase, you know you've got an oxygen enrichment problem now, which poses a combustible problem for you. It enhances combustion. So a lot of oxygen in the environment is not a good thing. Carbon monoxide. I put 2 numbers here, meaning 2 scales, 0 to 500 parts per million, 0 to 2,000 parts per million. Draeger makes different sensors that can go lower concentrations full scale or higher concentrations full scale. We're monitoring in the parts per million range. 1 part per million is 1 part of gas per 1 million parts of air. Okay, so it's a very minute amount of gas. Hydrogen sulfide, again, we're monitoring in the parts per million range. Generally, your scales are 0 to 100 in your multi-gas meters, but you can go up to 999 ppm if you'd like. The oil refineries like to have this in the oil production fields because they're dealing with very high concentrations of H2S when they're monitoring at the well. So that's why we have different scales.
Entry key 1, this is IC. I copy your readings on your gas monitor. Your entry time will be 11:38. IC, entry key 1. We are past 4 feet in, and all readings are the same. Entry key 1, IC, I copy.
Hey, located the victim. Copy. Hey, you there? Alright, go ahead and let IC know. Found the patient. About 20 feet in, came down a ladder, and then we're gonna use mobile. alert and oriented, and we have no need for any more equipment or anything. And then I see Entry Team 1.
Entry Team 1, I see.
I see Entry Team 1. We have made access to the victim. After about 20 feet in, we went down a short ladder.
I copy, you made contact with the victim, and he is ambulatory, and you're going to make your way out.
This has to do with gases, and of course I put on here the gases that this instrument, or these instruments, are detecting. I put MW up here, which stands for molecular weight, so that the firefighters know that if they walk into an environment that is a still environment, that the gases that you're looking for have different weights. And this here basically is representing a room, a simulated room, if you will. I put air in the center because air's molecular weight is 29 molecular weight. You'll see the carbon monoxide is at 28. It's just one lower. So for when you're making house calls and people have carbon monoxide issues at a structure, generally the moment you walk in the door, if you have an instrument that's just operating in passive mode, and when I say passive mode, I'm referring to an instrument that has no pump. The gas is just going through the membrane and hitting a sensor. You're going to pretty much detect that gas almost immediately in most cases, because its ability to diffuse in the entire structure equally is very good. But if you walk into a house where somebody has a natural gas issue, where they're smelling mercaptan, and you're going into the house to check for a methane leak, you may want to walk in with a wand if the environment is still, because methane has a molecular weight of 16. It's almost half that of air. So you may have to walk into a structure and go up to the ceiling and have the sample aspirated down, what we call a extendable probe, and wait for the gas to come down the probe through the hose to the instrument. If you have a sample draw meter, which you would have to have in this case, the pump would have to be flowing, and to see if there's natural gas that might be hovering underneath the ceiling of a given structure. If there's plenty of convection, meaning air movement within the structure, there's a good chance, if there's quantifiably a lot of natural gas in that structure, you'll be able to pick it up on your Draeger meter. And just to give you an idea on natural gas, 1% of the LEL equals 500 parts per million. So it takes 500 ppm to get the meter to go to 1% LEL. Okay, that's how the increments go. Methane is a great gas to talk about because it's good math. It's good math. Hydrogen sulfide, you can see, is heavier than air, 34 molecular weight. And in a still environment, such as a sewer, H2S will always be at the bottom of the manhole. That's why they call it the silent killer. Because you go down in a space, you don't really know it's there, you can't really smell it yet, and it's way down at the bottom, and then individuals take one hit of this and they're overcome by H2S. This was a common problem back in the 70s and even into the 80s. In fact, back in the 70s, H2S wasn't even a gas that they were monitoring for. It was mostly combustibles, oxygen, carbon monoxide came in. Actually, carbon monoxide came in after H2S. But combustibles and oxygen really were the two that were monitored for in most of the country. Then H2S came in because of manhole entries, and then carbon monoxide came in into the foregas because when city workers or sanitation workers were going down into manholes, or the gas company, what they did to purge the space is they would send a hose down, and here's the street, and they got a blower up here, and they're blowing air down into the hole to add oxygen to the space. Well, there's cars driving by up here on top, and they're taking the carbon monoxide that's being generated from the automobiles and they're introducing it to the space. And that's why CO came into being with the four-gas instrument. Just a little history there for you. I also put another gas here, hexane, which is 6 carbons and 14 hydrogens. That comes out to a molecular weight of 86. So you can see the difference of gasoline vapors in a still environment in comparison to air. And of course, being a vapor, it's going to be very heavy. Gases generally are lighter, like ammonia is a very light gas. Ammonia is almost equal to methane in molecular weight. It's at 17, not 16. Well, okay, the question is, how far can the instrument detect ahead of itself as you're walking into a structure without a pump? And in this given scenario, when you walk in the door, you're going to be picking up the air concentration in that space. If carbon monoxide is present, you're going to pretty much pick it up pretty quick. There's a term called fixed law of diffusion, which is a passive rate. Consider it the rate of gas traveling through the instrument without having a pump on, if you can think of it that way. In fixed law of diffusion, your fixed rate of flow is about 500 cc's. Without a pump. But the gas has to be present for the instrument to see it. So if I'm holding the instrument here, okay, but I've got a methane gas issue that in my head might be 2 feet under the ceiling, I may want to take the meter up here to do this, and then I can detect my natural gas. In some cases, I may have to bring it down to my feet to pick up hydrogen sulfide. These are just simulations. So the gas detector can only pick up the gas from where you have it sitting. So molecular weights play a big part in this, but remember, convection and air movement mixes all the gases up as well. And you have to have pretty high concentrations, again, to get your natural gas readings to move. Because you're dealing in a lower explosive limit scale, not a parts per million scale, which would pick up minute traces of natural gas. The one thing I want you to realize here, too, is that these instruments are detecting combustibles, CO, your oxygen concentration, and your hydrogen sulfide concentration. There's a lot of other gases and vapors out in the field that these instruments cannot see that could be hazardous to you. And you've got to remember this. And in the hazmat world, when they're entering an unknown, they're pulling out an array of instruments. And this just happens to be one of them. They might be pulling out an FID. They might be pulling out a photoionization detector. They might be pulling out Draeger tubes to make sure that they don't have any acids, that they don't have any other types of aromatics or ketones or freons. There's a lot of hazardous gases, and the other thing you've got to realize too is that all gases and vapors, some of them have a good warning property where you can smell them, and some of them don't have a warning property at all. And in fact, with that said, natural gas in its natural state has absolutely no odor to it whatsoever. And that's why they add mercaptan to it, so that you can smell it in your house, that you know you've got a natural gas leak. Carbon monoxide is truly the silent killer because it has no warning property. You don't really know it's there, and you're being asphyxiated as you breathe it. H2S does have a warning property. Literally at probably 0.1 ppm, you can smell it, and that's that rotten egg smell that you smell when you're driving down the road sometimes. Your catalytic converter can generate hydrogen sulfide. So your nose picks this up, and you know it's there. Gasoline vapors, you can smell that. You know it's there. So that's another thing that I needed to add to the training is the warning properties of these gases. I have a little band on my arm that says, "Be aware, use your air." And in the fire service, when you guys are walking into an environment that is suspect, in my opinion, take all the meters you want, but wear an SCBA because you don't know what you're walking into.
Hey, something's wrong with my pack. I can't breathe. Hey, check the bottle. Make sure it's on. Yeah, it's on. Nothing. No, this is okay. Cool. Hey, buddy system. cool. Alright, now let's just go ahead and get them out, alright? We'll just stay connected, and we'll just go.
And now I just wanted to show you that all combustible gases, whether they're a gas or a vapor, all have different lower explosive limits. And what I mean by that is exactly this. How much gas does it take before you have to have an ignition source and oxygen to create a combustion or an explosion? So you can see here's our typical methane that we've all been talking about, our natural gas, our methane, our CH4, 1 carbon, 4 hydrogens. 5% by volume is what we need to light the match, kaboom, okay? Here's propane, you only need 2.1% by volume for the explosion to occur. Here's pentane at 1.5% by volume. Here's hexane at 1.1. This is very similar to that of gasoline. Gasoline's LEL, I believe, is about 1.3, pretty close to that marker. Here's hydrogen at 4% by volume. And here's carbon monoxide that you think, and I know I said it early on in the presentation, we all think of CO as a toxic gas, which it is. But it also is a combustible. But you got to have an awful lot of it to create an explosion. And that's a lot of times in your fires, when you guys get your flashovers, this is one of the gases that's accumulated in an abundance of, that cooks with all the other gases that are in there that aid to that flashover explosion. It's a lot of carbon monoxide, 125,000 parts per million, which is a lot. Because I'll tell you what, 12.5% by volume in a space, you've displaced a lot of oxygen there, haven't you? Because you know what? In this scenario, the amount of oxygen, if you had 12.5% by volume CO in air, your readout would probably be somewhere around like 17.5 or right around that area of air in that same environment as CO. On the subject of oxygen, as we were talking about altitude, you'll notice when you turn on a Draeger meter, with the exception of the Exam 3000, when you turn the instruments on, generally you get 0 at LEL, you'll get 0 at CO, 0 at H2S, and your oxygen will pop up at 20.9. Okay? And that's if you're basically turning the meter on in the same neighborhood all the time. But if we leave here today and head up to Big Bear, or I should say Arrowhead for you guys, not Big Bear, Arrowhead, what's going to happen when you get up there is you're going to turn your instrument on and your oxygen readout is going to be lower. It's going to be down at maybe 20.2, 20.3, 20.4. And when you turn it on, that's an unacceptable start point. You've always got to start with a 20.9% on oxygen, always. And you always have to start at 0 LEL, 0 CO, 0 on H2S. If any of those numbers are not on those markers that I just called off, then something's not right. Either the meter has drift, which Draeger meters don't generally drift, or you changed altitudes. Draeger instruments on startup never perform a fresh air calibration by themselves as part of their pre-entrance startup. Okay? There are some manufacturers that do, but I think we pointed that out at 74s, that Draeger does not do that, and they do it for safety, because if you're in an environment where you might have a gas around you and that does not have a warning property and you're unaware of it being there, but it's creating a movement on your meter, you don't want to start your meter up and have it fresh air itself in that suspect environment. Let's just say you had 12 ppm of carbon monoxide in your environment, and my instrument does a fresh air cal for me automatically. Well, now 12 ppm becomes 0. And that means when I get up to 25, I really have 37. Okay? So that's not a good scenario. So if you turn a Draeger meter on and you see carbon monoxide, for example, up at 10, 12, 15 ppm after it started up, chances are that's how much CO you're standing in at that given point in time. And the best way to remedy the situation is to grab the meter, walk outside to a fresh air environment, and see what happens to that 12 to 15 ppm of CO. More than likely, it's going to go all the way down to 0. Okay? And the same with oxygen. If you're not reading at 20.9, what that's going to have to do is, if you've got your 0 on LEL, your 0 CO, 0 H2S, but your oxygen's reading 20.6, it's going to prompt you to have to perform a fresh air calibration after your warm-up. Okay? And once you do that, you make sure you're in fresh air, and this will then come back up to 20.9 as your start point. Okay? Now, could you be in an environment that is suspect oxygen, where it went to 20.6? Could you really be 0.3% below on oxygen? If you're standing outside, the answer is probably no. But if you're in a structure on startup, it's possible. It could be that there's some gases there that have displaced the O2 that your instrument can't detect. And you can't detect it with your nose because it doesn't have a warning property. It's a hypothetical, but when in doubt, take your instrument outdoors and perform a fresh air calibration. What you've got here is what's causing a deficiency when you walked into a space. Generally, when you're walking outdoors or you're walking to a structure, your oxygen content generally doesn't change much. It's when you get on a space or come upon a space that's a tank, a vessel, it could even be a ditch. A ditch is even a confined space, because if there's no air movement and everything is settled, you could have inert gases in a ditch that you don't know about that are much heavier than air. Sounds kind of odd, but it's true. But generally what happens to drive your oxygen from 20.9 down to your alarm point of 19.5, another gas has got to be there to displace that oxygen. The bottom line is this. It takes roughly 6% by volume, and this is not an exact figure, all right? So that's important you realize that. In the neighborhood of 6% by volume will drop your 20.9 O2 down to your A1 alarm, which is your latching alarm on your Draeger instruments. Okay? And this could be, that's why I said a cumulative gas or gases. It could be a number of gases that have accumulated together to drive your oxygen down. But in most cases, it's usually just one. And in a manhole, and I say manholes because when I grew up in this business, I grew up in the safety business. And for 20 years, I sold instruments to municipalities, water districts, sanitation districts, where that's what they do. They enter confined spaces, especially manholes. And if it's not carbon dioxide that's creating the oxygen deficiency, then it's a lot of H2S and a lot of methane gas that's creating the oxygen deficiency. So the whole idea of the Draeger meter is to make sure that when you get down to this 19.5 marker, you're getting an alarm. Okay? This has to do with your alarms. Now, this alarm chart is again on the Wheatstone Bridge catalytic sensor, your combustible detector. And what I've got here is 0 to 100% of the lower explosive limit, methane again. And this is talking about what I was just referring to. Here's 10% of the LEL, which gives you your A1 alarm. It means alarm 1. You will get a pulse. Okay? As the gas increases, you'll hit 20% of the LEL. Again, 80% safety factor to this point. Now you will get a double tone. Okay? And in addition, you'll notice that double tone If I heard a gas detector right now, and I heard that tone, I would know that I've got a severe problem.
An A1 alarm, A2 alarm. This is firefighter Gombiski on the second level. We have an A2 alarm. My LEL level is at 47. Hydrogen sulfide is at 19. My carbon monoxide is at 92. My oxygen level has dropped to 18.1. That's affirmative. We are pulling out. We are retreating.
Keep in mind, when you reach this A2 threshold, it latches. So once you exceed that 20% of the LEL, and if the gas improves to where it starts coming back down to 0, this alarm will keep alarming until you hit the OK button on the Exam 3000. On the multi-warn 2, it's the big Chuck Mangione flugelhorn button. And on the mini-warn, it's your entry button. They're all basically the big buttons on the instrument. And that will silence the alarm once the hazard has gone away. So I hope that explains the alarms. Now, one thing I need to make a note of, we're starting from a 0 gas up to full scale. So I didn't write carbon monoxide in here and hydrogen sulfide, but I want to talk about them a little bit. Carbon monoxide is a 0 to 500 ppm scale for CO. So your A1 alarm for carbon monoxide will be 25 parts per million. You will get your single pulse alarm, and 60 ppm is the A2 alarm for carbon monoxide on most Draeger meters, unless the user goes in and changes it. You can go in and change it, but 25 ppm on the A1 is pretty much a state law in California not to exceed. So that's your A1 alarm. A2, 60 ppm on carbon monoxide. That will be the latching alarm, and you'll also get your double tone pulsations. And then on hydrogen sulfide, you've got a 0 to 100 part per million scale. You'll get a 10 ppm alarm point, which will be your A1. And then 15 parts per million will be your A2 alarm, which will be your latching. Now, on oxygen, it's flip-flop. On oxygen, you're actually at 20.9, and in most cases, the deficiency of oxygen is the most common alarm. So you're talking about a set point here and a falling of oxygen. So the A1 alarm on oxygen, when you get down to 19.5, you're going to get an A1 alarm, but in the case of oxygen, the A1 alarm latches. So once you hit that 19.5, as you're losing oxygen, and then the oxygen then comes back up to 20.9, the A1 latches, and again, you've got to push the big button to silence it. On enrichment on oxygen, from 20.9 climbing up to say 22.5, 23% oxygen, you'll get an A2 alarm, but it is not a latching alarm. It's your single pulse alarm. So it's just vice versa on oxygen and only oxygen. This instrument is the Exam 3000 by Draeger, 4-gas meter. This instrument does not possess an infrared sensor. It has a Wheatstone catalytic hot wire sensor for monitoring combustibles in the LEL, oxygen, CO, and carbon monoxide, H2S, hydrogen sulfide. To turn this meter on, you hit the OK button, hold it down for a 3, 2, 1. Starts up. Notice the battery on startup was full. That's the way you check the battery on this instrument, if you want to check it before it turns on, is while you're pushing the OK button and it's going 3, 2, 1, you see that the battery was full. You can let go of the on button and it won't start up. So that's how you check the battery if you're only interested in checking the battery. Then it goes through its warm-up and it tells you where all the A1 alarms are and where all the A2 alarms are. A1 is your first threshold, A2 is your second threshold, and latching alarm. And this says I have 90 days before calibration is due. And then it gives me the gases. You'll also see that the readout on this meter compared to the mini-worn Draeger and the multi-worn 2 Draeger is a little bit different. Instead of it being stacked top to bottom, it's left to right, both on top and bottom. So on the top left, you've got your EX percentage LEL. Now that's different from your Draeger mini-worn, multi-worn. This does not read CH4, it just reads EX, EX for explosives. You also heard a confidence beep just there a minute ago because we have an arrow pointing to it. That can only be removed through CC Vision with a computer. Oxygen percent volume 20.9, H2S is ppm 0, CO ppm 0. Also the short-term exposure level is also on, and that can be turned off as well. So for a firefighter that wants to use this meter, here's what you do. The first thing you do, we have a little bit of drift on our CO, which I don't particularly like. So I'm going to do a fresh air calibration with this meter. That's going to be the first thing I'm going to start. But I've already noticed too that I have a full battery, and the battery is in 1/3 segments. So 33, 66, 99%, or 33.3, however you want to do it. But when you get down to one segment at the bottom, the instrument has to go into onto charge. So, fresh air cal, you have a down arrow here with an M for menu. The menu on this meter is a topical menu. It's on the exterior of the instrument. You don't go into an electronic menu like you do your mini-worn and your multi-worn. So I hit this button once. Fresh air cal is now blinking. I'm going to hit the OK button. And then all the sensors blink. I'm going to hit the OK button again. They continue to blink, but I see the word OK, which is telling me I'm going to have a successful fresh air cal. I hit it a 3rd time. And I wait for it to time out. I'm going to hit it a 4th time. And now it times out. Sometimes on the Exam 3000s, these touch pads, sometimes you have to hit them twice to get them to proceed. And they're a little touch sensitive. So I've done a fresh air cal. And now what I want to do before I use this meter is I want to perform a bump test. Now generally this is something I would do after a call, but today I'm just checking out my meters and I'm going to go ahead and give it a bump test because the chief wants to use this meter later on tonight for some testing. So what I'm going to do, again, a Draeger magnet. Here's your magnet right here, and it's that magnet that activates the internal pump on the meter. You also see that there's a cutout on this pump plate that mimics the pattern of the rubber boot that's on the exterior of the instrument. I should say parallels the boot, not mimics the boot. Again, a knurled knob, just like on the multi-worn 2. And my pump is on and I can hear it running. So, I am now going to get my cocktail cylinder and my demand flow regulator. I'm going to attach my demand flow regulator. I'm also going to check my cylinder composition, and it's exactly what I need. The proper amount of methane, hydrogen sulfide, carbon monoxide, oxygen as well. And my contents are certified until May of 2011, so I know I have a good cylinder of gas. Also with the pump running, you have to connect up a hose barb with a minimum of just a hydrophobic filter in place. This way, as the air is being aspirated in and then exiting this barb, I know that I'm not bringing any dust into the instrument, into the pump. So what I'm going to do now is I'm going to connect up my hose line to my cocktail bottle demand flow regulator. And I'm now going to connect my cal gas. And we're going to do a bump test here to see what our readings are like. Here we go. LEL, movement, CO movement, oxygen's dropping. There's our A2 alarm, which is our double pulse alarm. So far, the combustible detector is winning the race and is just 1 percentage point. It's already hit the 46 mark, so it has passed. H2S is gaining ground at 20. CO is also gaining ground. Once it hits 90, it's a pass. LEL is almost at 50, just hit 50. CO is at 90, H2S is at 22. So the only gas that's really lagging behind on this test, in my opinion, is the oxygen. It's reading 18.1 when it should be reading 17. So it's a little bit high. So I'm going to remove the gas. And I'm going to let this clear. Notice also above the battery icon are two little arrows, one kind of looping upwards, the top one looping downwards. That tells me that my pump is operational and flowing. So, the bump test on this meter was successful. I'm just waiting for the CO to clear. Now, at this point, what I can do is I can connect up my hose. I can connect up my probe. And again, I'm going to run a flow fault on this pump. In the event that I come up on a space where I have to monitor remotely, I want to make sure my intake is at the tip of the probe. There's all the dashes again from a flow fault choke off. And notice the two little arrows now have a line through the middle of them stating that the pump is choked off. The moment I remove my thumb, back to normal operation. And the CO will take a little bit of time to get back down to 0. But I can actually now, after I've done a bump test on the meter, my battery is good. I've checked the pump on the meter. We're back at zeros and 20.9. I can now use this instrument to go out and monitor in the field. However, one thing I would like to do before that is I'm going to calibrate this meter. And here's how you calibrate an Exam 3000. A little bit different than any other Draeger meter that I've ever seen. What I'm going to do is I'm going to take my down arrow and I'm going to hold it down all the way and keep holding it down. And then a password is prompted. Now the password on the Exam 3000 is 500 or 500. So I got to hit the up arrow to keep adding a number. And there's my 5. I hit OK to go to the second digit, OK to get to the third digit. So that kind of operation is somewhat similar to the single gas PAC 7000 in the way it operates. Then I hit it again. And then the arrow is now hitting one button cal on my exterior sticker. I'm going to go ahead and hit OK twice, maybe 3 times. There we go. You saw it took me 3 times to get it to move. Now, here are the numbers that the instrument is expecting. Notice that the oxygen is removed because when you do a fresh air cal, that's your calibration for oxygen. You do not have to blanket this with nitrogen to drive it to 0. So I'm going to hook up my gas. You don't touch anything. All you do is you hook the gas up while the numbers are sitting there staring at you. is hook up the gas, and when the instrument starts to detect the gas, it will start making its movements. And here we go. So there we go, we're getting our movements again. Wheatstone bridge sensor is really healthy in this meter. Waiting it to go up. H2S almost hitting the 20 marker. These sensors did well on the bump test, but I want to go ahead and just zero in the calibration. 91, 22, 52. So the numbers look like they've stabilized pretty good. We've been rolling for about a minute. So I'm going to go ahead and push the OK button. And there's my OK. Oxygen now comes back into the loop, although I'm really not part of it. And the calibration is over. And now we're reading our measurement menu, our instantaneous screen, and then we disconnect from the demand flow regulator. And again, this instrument has a tactile arm, ever so slight, but it does have a tactile arm to it. And then we'll wait for this to clear. I can actually at this point take the pump plate off, which will shut the pump off, and the instrument can now clear itself. As soon as the A2 alarms are done, then I can turn off that alarm, just like on all Draeger meters. So this will eventually go to 0, 0, 0 and 20.9, and you're all set. And that concludes the exam 3000.